to cover compared to what I set out. This is the first time I'm offering this course as a transport phenomena course, and so I'm interjecting heat and mass transfer as we go along. But what I wanted to cover in fluid mechanics is still not what I used to normally cover in a course. But let's see what we can do in the next today and on Thursday over about 2.5 hour period. In the last lecture, we looked at the thermal boundary layer, the development of the thermal boundary layer. And essentially, I am going at a faster pace, and I'm expecting you to fill in all the intermediate steps because the methods we have already seen, the scale analysis, the similarity transformation, etc. So I'm focusing on the concepts and laying out the path towards the final solution. And I expect you to fill in the intermediate steps. Okay, so in the last lecture, we basically looked at the boundary layer equation for energy. The previous two equations are for momentum. The Prandtl boundary layer equations are these two. We have already derived that through very careful scale analysis. That we did in detail. But when we looked at the energy balance equation, we just said following a similar procedure, you'll get this as your boundary layer equations. And the basic idea is that when you have boundary layer near a plate or near a solid wall, you will have a thin region over which a sharp temperature gradient or sharp concentration gradient would occur. And that is what we will call the thermal boundary layer thickness, which could be different from the momentum boundary layer thickness. And the two effective mechanisms that balance are the convection mechanism that is captured on the left-hand side in the flow direction and the conduction mechanism that is captured on the right-hand side in the normal direction. So what happens is heat is being conducted in the normal direction and it is being carried away in the flow direction. So these are the two balancing terms. And we saw that there is a strong similarity between equations 2 and 3. In fact, these two partial differential equations are exactly the same if I make nu as equal to alpha. But nu and alpha are properties, so I cannot find a fluid that has the same property. Very rarely you will find. But close to 1. For example, air has close to 0.73, so reasonably close to 1. And we also saw that if nu is much larger than alpha, the momentum thickness is much larger than the thermal boundary layer thickness, and vice versa. If nu is much smaller than alpha, the momentum thickness will be smaller than the thermal boundary layer. That's at the conceptual level. Then we said, okay, let's go and see whether we can solve the thermal boundary layer equation number 3 using similar ideas that we saw for the momentum boundary layer. That means introducing a similarity variable, which is eta as equal to x2 divided by square root of x1. That's the functional form. And of course, this is just a recap of the Blasius equation. But the new one would be this equation, which is the thermal boundary layer equation. That is equation 3. This is equation 3. After you subject it to the similarity transformation, subject to the boundary condition. It's a second order equation. It's a linear equation, but it involves f as an input. So the velocity profile must be obtained first, which is given in the form of Blasius solution. It's a tabular form. So take the table, put it in there. You can integrate that numerically if you choose to. But we also saw that we could integrate that analytically, and we obtained the solution as given in here. Except to note that this f is tabulated. So we need to evaluate this integral that you see here numerically, okay, as a quadrature. And so there are two integrals that you need to evaluate to get the temperature profile as a function of the similarity variable eta, but Prandtl number is a parameter in this problem. So different Prandtl numbers will have different curves. And this is a sample solution that we saw in the last class. Each one is for different value of the Prandtl number. Okay, and this material is not covered in your book, Burstewart and Lightfoot. I mean by that, this particular solution is not given there. But what he covers is the asymptotic limit. What happens when Prandtl number is very large? the large Prandtl number limit. What happens physically, you need to understand, is the following. This is your boundary, and you have a thermal boundary layer, and you have a momentum boundary layer like this. That is delta, and this is delta T. So the thermal boundary layer is much smaller than the momentum boundary layer. So the velocity field is going to look something like this. But because the thermal boundary layer is small, we are going to approximate by linearization the velocity boundary layer. Okay? And when you do that, we saw in the last class that the thermal boundary layer equation now becomes 3 eta squared, the coefficient that appears there. Previously, in the general case, there will be f that is appearing there, as you saw here. Okay? That's a general, that's valid for any value of Prandtl number. But when you make this assumption, Prandtl number is large, nu is large compared to alpha, the momentum boundary layer thickness is large compared to thermal boundary layer thickness. So near the thermal, and over the entire boundary layer thickness for the temperature, you can assume the velocity profile to be linear. And when you do that, you get a solution that doesn't require you to evaluate quadrature in terms of f, but still requires to evaluate this function, e to the power minus eta cubed d eta. There is no analytical integral for that. That has to be done numerically. Okay? That's where we stop. Now, are there any questions on that? What we need to do now is take these expressions. Remember, always when you're solving momentum equation, you get the velocity profile, but what you are really interested in is the forces, the drag force, for example, the lift force. In a similar way, when you're solving a heat transfer equation, you get the temperature profile as you did here. What you're really interested in is the heat flux or the Nusselt number. Okay? And in mass transfer, the same thing. You follow the same ideas, you get the concentration profile, but you're interested in the mass flux, how much of material is entering the domain through the boundary. So our problem now, using that velocity profile that we have, we want to calculate what is the flux Q. So this is our x1 direction, and that is our x2 direction, and this is our boundary layer. So how much of heat is being transferred into the flow domain from this boundary, from this plate? In heat transfer, as we saw in flow inside a pipe, there are two situations that one can normally encounter. In fluid mechanics, typically at a solid boundary, you have zero velocities. Okay? But in heat transfer, you can maintain this surface at a constant temperature, which is what we did right now, or you can maintain it at a constant flux. Both are physically realizable. How would you maintain a surface at a constant temperature? You have a condensing medium, steam condensing on one side of this plate. Steam condenses at a constant temperature, right? Or melting, phase change. Whenever you have a phase change, you have constant temperature. So you could have a tube, one side of which is steam condensing, the other side you're heating up some gas. Okay? So that way you can maintain a constant temperature. How do you maintain a constant flux? Electrical heating. Okay, so you just put an electrical resistive heating, and you can maintain certain amount of heat that you transfer Q. But what you need to realize is when you maintain a constant temperature, you don't know what the flux is. You need to calculate the flux. But if you're maintaining at a constant flux, then the temperature of the wall will change. You don't know what the temperature is. You need to solve for the temperature. But they are related to each other. So in this particular case, we are maintaining this wall at a temperature T0. Okay, and the fluid far away is at a temperature T infinity. The fluid that is entering is also at a temperature T infinity. So that fluid is going to get heated up or cooled, depending on T0 is greater than or less than T infinity. But the expression for calculating that flux Q is given by the flux Q evaluated on the surface, that is at x2 equal to 0 is the plate, multiplied by the differential area. The differential area is dx1 times dz. dx1 is the differential area in the x1 direction. dz is perpendicular to the plane. That's the area. So remember, Q has the units of so many joules per meter square second. It's the rate of heat transfer per unit area. Multiply that by the area, you get joules per second. So this Q is the actual amount of heat that is transferred from the plate into the fluid over a certain length of L. Okay, L is the length. So the integral is found from 0 to L, 0 to W. W is the width perpendicular to the board. And the flux evaluated at the bottom plate multiplied by the area. Now flux is given by Fourier's law, which is minus K times dt dx2, the normal temperature gradient evaluated at x2 equal to 0. Okay, and in doing that, going from this step to next, I have taken out 2W. How did I get the 2W? Why did I get 2 there? This is as given in your book, so I kept the 2 there, but it is, you need to understand the implication of it, the meaning of it. The integral is given in your book as 0 to W, so the length, you're doing both sides. That would be the interpretation. Top, so you're maintaining, in fact, if you remember the figure from the last lecture in your book, he had a boundary layer going that side and a boundary layer going that side. And this plate is maintained at a constant temperature. So from the plate, you are having heat flux to both sides. Okay, and that's why you get the 2. And 0 to W, none of the quantities in this expression depend on W. So 0 to W dz simply becomes W. Okay, and this flux does change from point to point in the x1 direction. Why does it change? The flux depends on the temperature gradient. The temperature profile is going to be something like this, right? So the gradient at this point is going to change from point to point. So this will be a function of x1. This whole thing will be a function of x1 evaluated at x2 equal to 0. And that integration has to be done properly. Okay. So how do we do that? We use this chain rule. dt dx2 is equal to dt d eta dx2. Now we know the relationship between eta and x2, the similarity variable. So you can take the derivative and then dt d eta you can calculate from where? That's where you use this. Okay, dt d eta, this is a function of eta. Okay, so in fact it is done in dimensionless form, d theta d eta. Okay, so that expression is going to give you a way for calculating the derivative, d theta d eta. Now, how did I go from dt dx2 to d theta d eta? What did I do? I just took dt dx2 and wrote this as d dx2 of t minus t infinity divided by t naught minus t infinity. Then I wrote that as d theta dx2. But I've divided by t naught minus t infinity, so I need to multiply that also by t naught by t infinity to keep this thing same. Now I subtracted t infinity, but that doesn't change anything because I'm taking the derivative of t infinity with respect to x2. So it appears within the derivative term. Okay? So those are exactly the same expressions after you have taken out this t0 minus t infinity. Okay? And then the k comes out there, and the L will come out when you do the non-dimensionalization of x1. Okay, and that's all you need to do. Then carry out the simple integration with respect to x1 of this. Everything else is a constant, and put it in dimensionless form. You get this result. Notice here, this whole thing is a constant. And let me ask you a question to see whether you have read from last lectures. What is that C? The constant C that appears there. Do you remember from last lecture? It's a linearization constant for the velocity profile. Okay, when you linearize the velocity profile, there is a constant that appears there. That's C. And what is this one? Very good. It's a gamma function evaluated at 4/3. It's essentially an integral 0 to infinity of the exponential function. Okay, so when you are, one of the important things, I guess, in a graduate course, this is, we are now at the tail end of the course, is for you to develop this confidence. When you open, there's no way that we can cover everything in Burstyn and Lightfoot in one term. Okay, so I'm kind of laying out all the major ideas, and then there are a number of other problems. When you go and open the book and study for your general exam, when you see something like this, you should be able to figure out how we go from this step to this step. How do we go from this step to this step? Okay. And the last step that we want to do is on the left hand side, remember we have Q. Q is equal to this big expression that we have on the right hand side. But Q can be defined as a heat transfer coefficient multiplied by the area multiplied by the temperature driving force. Okay. So Q can be evaluated either from the temperature gradient or by introducing the heat transfer coefficient. Okay. So in a heat exchanger design, all we want is a heat transfer coefficient. Then we would prefer to use the simpler formula if I know what the heat transfer coefficient is. That heat transfer coefficient must be obtained by solving this complicated problem that we have done or going directly to the lab and measuring everything else and figuring out what the heat transfer coefficient is. Finally, the result is presented as a dimensionless correlation for Nusselt number, which has the heat transfer coefficient HL over K. L is a length scale, K is the thermal conductivity, H is the heat transfer coefficient introduced in this equation. You should look at this equation as the equation that defines what a heat transfer coefficient is. So that is equal to, when you evaluate all these constants, you will find that it is equal to 0.677 times PR to the power 1/3 RE to the power 1/2. RE is the Reynolds number based on the length of the plate. Okay, so in a heat transfer course at the undergraduate level, I'm sure you would have seen a lot of these correlations. One for horizontal plate, one for vertical plate, one for tube, for rectangle, etc. They are often presented in this form. Nusselt number equals a constant, Prandtl number to the power something, and Reynolds number to the power something. And graduate level course basically reveals how this is obtained, at least for laminar flow in simple situations. Okay? So this is valid only for large Prandtl number case. Any question?
What's the range for a large Prandtl number?
What is that?
What do you consider a large?
What do you consider a large? Anything that's greater than 1, you can treat it. So 10 is good enough. That would mean that the boundary layer thickness for thermal one is 1/10 of the boundary layer thickness for the momentum. Okay, so if that is the case, you could use this result. Any other questions? Okay, I'm going to go through again because it's important for you to be exposed to this one common integral method. It's the same problem. Again, this is from Bert, Stewart, and Lightfoot directly. Okay, do you remember what one common method is for momentum integral? How did we do that? What was the basic idea? Exactly, that is the key idea. Okay, so you integrate it in across the boundary layer, so you lose the ability to predict the velocity profile. So you assume a velocity profile, and when you assume a velocity profile, you put that velocity profile in the integral form of the momentum equation. So this is the integral form of the momentum equation. So you put in what the velocity field is, and then solve this equation everywhere. Okay, you put this and solve that equation. That will give you the boundary layer thickness growth, and then you can predict what the shear stress is. You can predict what the friction factor is. So the idea then is we should be able to do the same thing for the energy equation as well, using the same steps. Replace V2 in terms of V1 from the continuity equation, do integration by parts, and you can show that the boundary layer equation for energy reduces to this particular form that you see here. Okay. Now you need to input what the temperature profile is in both places. You need to assume and you need to input that. Then you can solve for the thermal boundary layer thickness, which is going to be different from the momentum boundary layer thickness. Okay. And then the steps are exactly the same. I'm guaranteeing, I want you to study this. I'm going to have one question on this problem in your final exam. Okay. Even though I've not given you a lot of assignments on these, you should be able to handle one common integral method, either for velocity profile or for thermal or for concentration problem. Okay, so study this, please. Now, those are the two equations that I just showed you here. Okay, one for the momentum and one for the energy. These are the integral form of the conservation equations. You should know how we obtain that. And as you pointed out, what you need to do now is assume a velocity profile. We did this with a cubic velocity profile, I believe, when we looked at the one common integral analysis for momentum thickness. The velocity profile is arbitrary. You assume something. So in this case, in this example, he shows you one with a quartic profile, a fourth degree polynomial. Okay, and y is the distance in the vertical direction, and delta is the boundary layer thickness, momentum boundary layer thickness. So as y goes to delta, the velocity field goes to the free stream velocity field, that is Vx over V infinity goes to 1. The same assumption you make for the temperature boundary profile, a fourth degree polynomial, but delta T here refers to the thermal boundary layer thickness. They are allowed to be different. Okay, so these are assumptions. Assume a profile. Once you assume the profile, you take that and put it into the equations. So I guess we have it here. Okay, so here what he shows is only the right hand side. Let me just flip back once more. So the right hand side requires this integral, one for velocity and one for temperature. So plug in the profile and evaluate those integrals, and that is what is shown here. Integral 0 to infinity rho Vx, V infinity minus Vx dy. What is that right hand side? So for Vx, this particular term, you have this, which is the velocity profile assumed. Then for the next term, V infinity minus Vx, it is this part. An integral is with respect to dy. Okay? And you carry out this integration. It's a fairly easy integration to do, even from an exam point of view, because all you need to do is take integral of x to the power n, for example. So here, eta to the power 8 you might have when you take these two terms, and then put the limit between 0 and 1. The limit is between 0 and 1. So you'll get this expression, 37 over 315 rho V infinity square delta x. That's the right hand side of that equation. Do the same thing for temperature profile. Okay, and here you notice that there is a velocity there and there is a temperature there. Okay, so when you are taking the velocity expression, that's going to be the first term, and when you take the temperature, that's going to be the second part of the term. And the integration is with respect to eta. So what he has done, maybe I should ask you, can you explain how I get the delta here? What manipulation has been done to get the delta? In the second equation, the integration is with respect to dy, that is d eta t. Okay, across the thermal boundary layer, because this is the energy equation, the integral is across the thermal boundary layer. But the expression for the temperature profile is already given in terms of thermal boundary layer. But the expression for the velocity, which is the first term appearing here, is given in terms of delta. Okay.
Is it the difference between the thermal boundary layer and the momentum boundary layer?
The difference or the ratio. It captures the difference between that, but it is basically the ratio. So what you do here is multiply and divide by delta t to the power 4. Okay, and then you'll get y over delta t, and delta t over delta is defined as the this symbol. That's also called delta in Greek. This is the lowercase delta, that is the uppercase delta. Okay, so the uppercase delta is nothing but the ratio. In fact, it's shown here clearly. Okay, eta is defined by y over delta. Eta t is defined as y over delta t, which you can write as y divided by delta with a capital delta in the denominator as a ratio of the two boundary layer thickness. Okay, why would you want to do that? Because you want the integration in terms of the thermal boundary layer thickness eta t. Okay, so the temperature profile is already in terms of eta T, but the momentum thickness is in terms of eta. So you need to convert that in terms of eta T. And that's what introduces this delta to the power 4, delta cube, etc. So please go through this, and if it is not clear, come and see me. Okay, I want you to be prepared on this topic. And so this equation simplifies to, after you carry out the integration, plug it into the momentum equation and carry out the integration, this becomes that. And the energy balance equation becomes this. So you get the boundary layer thickness for momentum and thermal as a function of Reynolds number. So this essentially captures the Reynolds number and the Reynolds number and the Prandtl number. Okay, so the only thing that we don't know in here is what this delta is. What is delta? Delta is the ratio of the momentum thickness to the thermal thickness. Okay, we know that as a ratio, but we don't know what it is. Okay, so we take this expression and plug it into take the ratio of this, that is 12.412 divided by 12.413, because that ratio is delta over delta T. That is your capital delta, so that is going to be your capital delta. So by dividing that one by the other and squaring it, you can simplify that equation into this equation, which is now parameterized in terms of Prandtl number. So if I know the Prandtl number, I can solve for this. So this procedure for computing quantities now would be, your starting point would be this equation. You find out what is the Prandtl number, because that's given by the fluid. So you know what the Prandtl number is. You calculate this delta out by solving this polynomial. Okay. Once you know the delta, you put this in there. You know the boundary layer thickness for temperature, and you know the boundary layer thickness for momentum. And then you can use that in your profile, calculate the derivative, calculate the flux, the heat flux, the Nusselt number. Okay. That's the purpose of doing this calculation. Now it turns out that the solution to this for small value of small value of delta is approximated by this expression. Delta is the same as Prandtl number to the power minus 1/3. The two curves, if you plot this curve and if you plot this curve, they will lie on each other. So it's a good approximation to the expression that you have in equation 14. So using that and following the same procedure as we did before just now, take Q, evaluate the flux, and put it in terms of Nusselt number, and you'll find through the integral analysis the same result. It is Prandtl number to the power 1/3, Reynolds number to the power 1/2. Of course, there is a coefficient. That coefficient will be slightly different depending on what kind of a temperature profile and velocity profile that we assume. So all these results lead to the same path. The functional form for Nusselt number dependence on Prandtl number, Reynolds number for laminar boundary layers is Prandtl number to the power 1/3, Reynolds number to the power 1/2. Okay, that's the key result that we get analytically. Any questions? Yeah.
For the case of velocity using the one-farm analysis, we found the shear stress and also the friction factor.
Yeah.
Extending that analogy, what exactly are we finding using the thermal and the concentration cases?
Okay, good question. So in the case of a velocity profile, we assume a velocity profile, you get the shear stress, you get the friction factor, right? In this case, we are assuming, because the temperature profile depends on the velocity profile, we need to assume a velocity profile and a temperature profile. Okay, but our goal is to predict the heat flux. Just like the shear stress at the wall is our goal for momentum equation, it's the heat flux. This should be K. The heat flux at the wall. That is our goal. So we need to assume a temperature profile, but we also need to assume a velocity profile, because the heat transfer problem depends on both velocity. It's a convective heat transfer problem. Depends on both velocity and temperature. So we assume that, and we solve for the heat flux at the wall. You integrate the heat flux, you get the Nusselt number. Now, friction factor for fluid mechanics is the same as heat transfer coefficient for heat transfer problem is the same as mass transfer coefficient for mass transfer problem. Okay, you should know this analogy: F, H, and K. Okay, and in the case of the molecular process, it's mu, it's the thermal conductivity, I guess I should call it Kg, and this is the diffusivity. So this is the similarity in the constitutive equation for molecular processes. Momentum transfer is governed by viscosity, heat transfer by thermal conductivity, mass transfer by diffusivity. But the macroscopic quantity that we are interested in computing is the friction factor for fluid mechanics, heat transfer coefficient for heat transfer, and the mass transfer coefficient here. Now, if you want to talk about the dimensionless number, F itself is the dimensionless number. But for heat transfer, it is the Nusselt number. For mass transfer, it is the Sherwood number. Okay, that's what we are interested in predicting by the analysis. Is that your question?
Yeah.
Yeah. So the process involves assuming a velocity field, temperature field, solving this equation for the thermal boundary layer thickness, and then put it back in here and evaluate the flux. And the flux evaluation is shown. So recapping, this is where you assume the velocity, this is where you assume the temperature, and then carry out the integration required on the right hand side and plug it into that equation, and you solve for the boundary layer thickness, for the momentum and the heat. And this still has one unknown, and that is the capital delta. So we get the delta by taking the ratio of these two equations, which is delta, and you get this equation. Okay? So that delta is an unknown in terms of the Prandtl number as the parameter. So different Prandtl numbers will have different, which we know already, different Prandtl numbers will have different ratios of thickness, momentum to heat boundary layer thickness. And that's what this equation captures. And it is approximated by an equivalent equation. Delta is equals Prandtl number to the power 1/3. And if you use that, and then the second step is calculating the heat transfer rate from the flux, using the velocity profile and the temperature profile that we have just solved for. Okay, and that you get the Prandtl number to the 1/3 and Reynolds number to the power half. So the goal in all these problems, the three kinds of problems, momentum, heat, and mass transfer, is to get the frictional force, the pressure drop, and in the case of heat transfer, to get the heat transfer coefficient or the heat flux. In case of mass transfer, it is the mass transfer coefficient or the Sherwood number or the mass flux. Okay, so that completes boundary layer. Again, a good reference for boundary layer is the book by Schlichting. The entire book is devoted to boundary layer theory. Okay, but I will hold you responsible for everything in Burstyn and Lightfoot, particularly the problems from the end of it. You should be able to handle. The next topic that I want to talk about, we will take about a 5-10 minute break at the 1 hour mark or so. Okay. The next topic, which I hope I will start and finish today, is hydrodynamic stability. Okay. Right from the beginning of this course, when we were talking about solving for pipe flow, the parabolic profile, we asked the question: does that profile remain valid for any Reynolds number? And the answer we sought was experimental evidence suggests that it is not. After a Reynolds number of 2100, that parabolic profile fails to be observed in an experiment. And same thing with boundary layer theory, for example. When you increase the Reynolds number and you increase the length of the plate, the boundary layer breaks down to turbulent boundary layer. So next class I'm going to devote entirely to turbulence, but today I want to talk about how do we detect when a particular flow transfers from laminar flow to some transitional flow on the way to turbulent flow. So this topic deals with the idea of stability. Okay, so you might have seen this, particularly those in process control. This would be very simple for you. Others, the problems are simple, but you can expect one type of problem of this type I'm going to do today. First, the concept of a stability. Okay, so here let's take a concave parabolic dish kind of a thing, and in here I put a small ball, a spherical ball, and it is in its equilibrium position. We call that position a stable position. Why? Because if I perturb it, if I apply a force and kick it from its equilibrium position, it's going to return to that equilibrium position, maybe in an oscillatory phase. Okay? As the what causes it to bring back to the equilibrium position? Why doesn't it oscillate forever? Friction. Okay? So there is a dissipative mechanism. The friction brings it back, dissipates the energy, so the energy is finally brought back to its level of minimum potential energy, for example. Now, if I have a situation like this, convex parabola, and on top of that I have a sphere that is in equilibrium again. I have aligned it so perfectly that the vertical force is balanced by the weight is balanced by the supportive resistive force. Okay? Now I give it a gentle push. What happens to that? It moves away from there. If I give it a kick, it will just roll away. I don't know where it goes. Okay? That equilibrium position will be called an unstable equilibrium position. The concept here is small perturbations. If the system is restored to its original position, we call it stable. If it goes away from that equilibrium position to somewhere else, then we call that equilibrium position as an unstable equilibrium position. Now, it might happen that this has a valley like this, and then in which case it will come back and reach a new equilibrium position. So I kick the system, the unstable system takes it away from there and goes into a new equilibrium position. If I have a flat surface, then I would call that as a neutrally stable system, meaning if I kick it, it just rolls and stays in the new position. Okay? So every position is a possible equilibrium state in a sense. Okay? That we will call a neutrally stable situation. This is called a non-linearly unstable situation. Can you kind of explain what that means? Non-linearly unstable situation?
You can move away the energy applied as like, but it can come back if it is not.
That is the key. Okay? Non-linear, linear means small perturbations. If I make small perturbations, if it comes back, I call that as a linearly stable. We will understand why, because we are going to linearize the equations of motion. Okay? And that's why it's called linearly stable. So all these cases are addressing linear stability. But the last case addresses a nonlinear stability in the sense, if I make a small perturbation, it will come back. But if I give it a large perturbation, very large force, it's going to go to somewhere else. Okay? So we call this non-linearly unstable. Linearly stable, but non-linearly unstable. Any questions on those concepts? Have you seen this before? Yeah?
Last one is linearly stable.
You would call that as linearly stable because small perturbations will restore it to its original position, but non-linearly unstable. Have you guys seen these ideas in physics? Okay. So the next question is, have you seen the mathematics behind it? Okay. How do we, and I'm sure you have seen this in process control. How many of you have not taken a process control course? Okay. If you have not taken that, then this concept may be new to you, but those who have done would have seen it in a different context in terms of Nyquist stability criterion and stuff like that. I'm going to take a series of examples, and these are models. So I would call this as a differential equation a model. Now, Navier-Stokes equation is a model for fluid systems. Okay, so this could be a model for a reaction system. It could be a model for any dynamical system. A dynamical system is one that evolves dynamically with time. So time is the independent variable, and x is called a state variable. Now, what is a state variable? A state variable represents the state of the system. In fluid mechanics, what could be a state variable? U, V, W, P, velocities, pressures, or states, represent the states of the flow system. Okay? So in this case, X represents some state of the system. A we are going to call as a parameter. In fluid mechanics, what are the parameters that appear in the equation? Viscosity and density, mu and rho. Okay, or if you put it in dimensionless form, maybe Reynolds number. Okay, and this is a first order differential equation, so you need to have at least one initial conditions when you're doing the integration. So that condition is given at t equal to 0, x is equal to 0. Okay, so the right hand side of this equation I'm going to represent as some non-linear function. In this case, is it a non-linear function? Where is the non-linearity? X squared, right? So that makes it a non-linear function. So the question is, what do I mean by a solution to this differential equation? I mean a curve that is plotted as x as a function of time. So I have some initial condition. From that initial condition, this thing evolves. Maybe it will reach a steady state like this, or maybe it will reach an oscillatory state like this. It never reaches a steady state, and that is what I would call a solution. A solution to this problem is x as a function of time. That function satisfies this differential equation and satisfies the initial condition. This f could be any nonlinear function. Okay, we're going to take a series of examples and see what are the responses for each case. What do I mean by a steady state solution to this particular problem? How do I get a steady state solution to this particular problem? You set dx dt equal to 0. That means you set f is equal to 0. Okay, so find that value of x that makes this function f equal to 0. That's your steady state. Okay, and then ask the question, I'm going to take that steady state and perturb it. If I perturb it, does the solution go back to the steady state or go away from the steady state? We're going to do this mathematically to know whether the system is stable or not. Okay, now how many solutions can it have in general, steady state solutions? How many solutions can this particular problem have? Two, because it's a quadratic, right? It will have possibly two steady state solutions. It's possible that it will have no solution at all. That depends on the value of the parameter that I put in. Okay, but in general, if I have an unknown or a complex arbitrary function, a priori I don't know. Still, the theory is not advanced, so that I cannot predict how many steady states I will have. Okay, that's a challenge. So, as we said, I'm going to find first the steady state solution. That means I'm going to set dx dt equal to 0. That means f equal to 0. And the equation, if you remember, is a minus x squared equal to 0. I put a subscript s to indicate that it's a steady state. Okay, so xs is equal to square root of a plus minus. Those are the two solutions. Okay, so that is the steady state solution. What this tells me is the steady state solution depends on the parameter a. So if a is negative, do I have a solution, a real solution? No. Okay, so this kind of a diagram is called a bifurcation diagram, which simply says the state x plotted against the parameter a. So in fluid mechanics, it will be the velocity plotted against Reynolds number. What are we interested in answering? In answering the question, is there a critical Reynolds number above which a particular flow becomes unstable? When it becomes unstable, what happens to it? That is the path towards turbulence. Okay, and that's what we are interested in answering. Before we go to the Navier-Stokes equation and do these, it's going to be very complicated. We want to learn and practice with a simple ordinary differential equation. So the curve that you see in the top, okay, is a curve of solutions for various values of a. If I put a equal to 1, then I get a solution x is equal to 1, plus 1, or minus 1. Oops. Minus 1. Okay. Similarly, I put a different value of a and I get a different solution on this curve, or different solution on that curve. So there are two solutions possible for various values of a as long as a is greater than 0. If a is less than 0, there is no real solution. Okay. Now, what are these arrows indicating here? The arrows indicate that the solution in the green line is stable, meaning if I have a perturbation somewhere here, I start, the solution will go towards that equilibrium position. If I start somewhere here, it will go towards that equilibrium position. This indicates that the solution is unstable. So even if I start very close to it, it's going to go away from there. If you start very close to it on the other side, it's going to go away from there. When it goes away, it goes to the nearest stable solution. It is possible that there is no stable solution, okay, and we will see that case later on. So to understand that diagram plots the state against a parameter in the problem, and at a critical value of the parameter, the behavior of the solution changes. In this particular case, the critical value is a equal to 0. For a less than 0, there is no solution. A greater than 0, there are two solutions. One is stable, one is unstable. How do I know that? How do I know? I just made the claim that the upper solution is stable, but the lower solution is unstable. How do I mathematically show that? The concept is I perturb the steady state and see whether the steady state goes back. The trajectory goes back to that particular steady state. Okay? So this is how we do it. Perturb it slightly and examine the dynamic response of the system. Okay? Here is the key idea of linearization. Those who have done control would have seen this before. Okay? X of t is called the trajectory of the differential equation, the state. Okay? So I'm going to decompose that into xs plus x prime. Xs is the steady state, x prime is the departure from the steady state. So graphically, what does it mean? It simply means if I'm somewhere here, this distance is my x prime. Okay, the total state x is equal to xs plus x prime. Xs is a constant because it's a steady state, right? X prime is the departure from there. So if you want the steady state to be stable, what do you want x prime to be? Going to 0. No matter how far you push it. For example, if I'm in this steady state and I'm pushing the system to somewhere there. So initially I give an x prime, a departure from the equilibrium, and I want that x prime to be decaying. So when I plot x prime versus time, this initial value for x prime gives me the magnitude of the perturbation from the equilibrium state. And how do I want the curve to be? Exponentially decreasing. Okay? If x prime remains constant, what do I have? A neutrally stable system. If x prime goes like this, what do I have? An unstable system. So I've reduced the problem to finding what is the behavior of x prime, the perturbation away from the steady state. Okay, so xt is decomposed into xs plus x prime. And I take this and put it into this equation. I have this equation dx dt equals f of x with the parameter a. So wherever I have x, I'm going to replace this by x prime, xs plus x prime. So if you see on the left hand side, I write it instead of x, I write it as xs plus x prime. And for the function f of x, I also write it as xs plus x prime. Now what is the derivative of dxs with respect to dt? 0, because xs is a steady state, it's a constant, right? So what I will get is only dx prime over dt on the left hand side, because this is 0. Derivative of xs with respect to time is 0. On the right hand side, what do? I do a Taylor series expansion around xs, treating x prime as a small perturbation. This is where the idea of a linear stability comes in, because this function is a nonlinear function. I have a nonlinear Taylor series expansion. The first term would be f of xs. The second term would be df dx evaluated at x of s multiplied by x prime. You're all familiar with Taylor series, right? You're familiar with that equation, Taylor series? Yeah? No? You've seen it before. Do you have a graphical picture of what Taylor series is? If I ask you to explain Taylor series, how many of you cannot do it? What is Taylor series? No? Taylor series is a way of constructing an approximation to a given function. Okay. So if I have some function f of x as a function of x, the function is highly nonlinear like that. Okay. And I want to construct an approximation to the function around certain point, some reference point x. Let me call it xs. Okay. The simplest approximation that you can do is that function is constant everywhere, right? So you take that value of the function evaluated at xs and say that is my function everywhere. Okay, it's going to be a poor approximation except at the point xs. Now you can do better than that by saying, well, I'm going to do that and I'm going to draw a tangent to the curve, and I'm going to take the tangent to be the approximation to the actual function. What does that mean? Mathematically, that means f of x is equal to f of xs, the actual value, plus the derivative of the function df dx multiplied by the departure from that is multiplied by x minus xs. What does that second term tell you geometrically? The first term, if you truncate the Taylor series here, it says the function is approximated by horizontal line, which we know is 4. The next best thing that we can do is take a straight line. So that function plus the rise that you get from there, which is calculated based on df dx, slope multiplied by how far away you are from there, which is x minus xs. That gives you the rise. So you are adding a correction to f of xs. Okay, but once you get the idea, the tail is the next. How do you improve it further? It's not a constant. It's not a linear. You can say it's a quadratic, right? So you can then take not only the slope but the curvature of the original function. So the next term would be d square f dx square evaluated at that, multiplied by x minus xs squared. So that series continues on. So as you take more and more terms in the series, the approximation becomes better and better to the original function as you go farther away from the reference point. If you're close enough to the reference point, one or two terms in the series would be enough. If you want to go farther away, you need to take more and more terms. And Taylor series is an infinite series. Okay, that's a geometrical interpretation of what a Taylor series is. Now, in this particular case, this HOT means higher order terms. Okay, so I'm taking only the first two terms. In linearization, you stop there. Why? Because the next term is a quadratic. It's a nonlinear term. Okay, so we want to linearize that. So by assuming these perturbations to be small, we can neglect the higher order terms, and that process is called linearization. Okay, so what we have done is we have decomposed the state into xs plus x prime, put it on the left hand side. So on the left hand side you get only the variation of the perturbation with time. On the right hand side, what would happen to the first term, f of xs? 0. Why? Because that's how we find xs, right? We find x as that value which satisfies f equal to 0. So that function is 0. Okay? So this j is called the Jacobian, which is nothing but the derivative of the function at the steady state. This control people normally do. Okay? You construct the states. This is what you call a state space model, for example. Okay? Multiplied by the perturbation. And the higher order terms are neglected. So this is a linear equation, and you should be able to do it in your final exam or a general exam. Okay? It's a linear equation. Given a nonlinear equation, find the steady state, linearize it around the steady state. That means find that value of the Jacobian at the steady state. Okay? Now you have an equation. This is the first order equation. What is the solution to that? The solution to that is given in terms of an exponential, because basically you have dx prime dt equals sigma x prime or lambda x prime, whatever you call it, that constant. That constant is nothing but the Jacobian in this case. Okay, so the solution to that for x prime is going to be a exponential one, e to the power lambda t, for example. If you take that and plug it into the differential equation, what do you get? On the left hand side you will get lambda times e to the lambda t. On the right hand side you get lambda times e to the lambda t. It satisfies automatically. So when would this solution for x prime be stable? That is the solution. When would that be stable? If lambda prime is if lambda is negative, the real part of lambda is negative. Lambda can be complex, okay, and that is called the eigenvalue. Now here I have only one equation. If I have three equations, what happens? The process is exactly the same, but the Jacobian that you will get here will be a 3 by 3 matrix, okay, so it is equal to having a third order differential equation. So you will have three characteristic roots of the third order differential equation, which are your eigenvalues. So what you want is none of the eigenvalues should have a positive real part, because a positive real part means it grows, the perturbation grows. The negative real part means it decays. So the condition eventually is reduced to solving an eigenvalue problem after you linearize your dynamical system and making sure that all the real parts of the eigenvalues are negative. Then you are guaranteed stability, because the perturbations will die. Okay, that's the basic idea of linear stability analysis. It's called a linear stability analysis because we are neglecting the higher order terms. We are linearizing the original differential equation. Okay, let's do that analysis now for this particular problem. For particular this example, the eigenvalue lambda is nothing but the derivative of the function with respect to x at xs. The function is a minus x squared. That is your function. So what is df dx? Minus 2xs. Right? So that is your Jacobian. But we know what xs is, the steady state solution. One solution has xs equals plus square root of a. The other one has xs equal to minus square root of a. Remember, these are the two solutions that we plotted. Something like this. This one corresponds to plus square root of a. This one corresponds to minus square root of a. But notice that the eigenvalue is given by minus 2xs. So when you take this steady state solution xs, put it in there, what happens for this solution for the eigenvalue? It will be negative. That's why we say the upper part of the solution is stable. Okay? If the lower part has minus square root of a, so when you put that, there is already a minus that flips the sign, that makes the eigenvalue to be positive, and that's what makes this to be unstable. That's how we determine the stability. So we have seen a lot in terms of concept. Given a dynamical system, how to get the steady state, how to map the steady state as a function of the parameter, which is your bifurcation diagram, and how to locate the critical points. In this case, this is a critical point. And beyond the critical point, the stability behavior changes. In this case, there are two solutions, one of which is stable, the other one is unstable. And we get that by doing a linear stability analysis. Any questions on that particular problem?
If you have some equal to 0, what happens to that stability? Like you have, for example, you have 3 eigenvalues, 2 of them are negative and 1 is 0.
That's a good point. That's in fact what would happen right at this critical point. For that value, in fact, when you put xs a equal to 0, what happens to the eigenvalues? They're 0. Okay, so that would be a neutrally stable system, or a system where the stability changes. That will be a critical point. This is called, when the eigenvalue is 0, what can you say about in a 3 by 3 system we are talking about, right? What can you say about the determinant of that matrix? What is the determinant of a matrix? Do you remember? If I give you all the eigenvalues of a matrix, the determinant is nothing but the product of all the eigenvalues. So if one of the eigenvalues is 0, the matrix itself becomes singular. Its determinant is 0. Okay? And this whole area of bifurcation theory is about locating such critical points. In fact, if we want to find out the critical value of Reynolds number where the stability changes, we will look for that particular condition, that one eigenvalue must be 0. Okay, exactly one eigenvalue must be 0. Now, what happens if there are two eigenvalues that are 0? Okay, it leads to more complicated dynamical situations, which are beyond the scope of what we can do in this course. Okay, but it's a very perceptive question. Any other questions? Are you ready for a break? Let's take a 10-minute break and then come back and continue. with the stability analysis. So we'll meet in 10 minutes. Let me stop that record.